Hi everyone, and welcome to the fourth lecture about a model in topological string theory. Melissa, please go ahead.
Oh, thank you very much. So last time, we start to discuss the remodeling conjecture. Yeah, we gave an overview of the conjecture, so that I will call section 3.1. So then today I'm going to provide details. So first, so recall that the remodeling conjecture can be viewed as, so maybe let me, the remodeling conjecture. It can be viewed as a version of O-genus mirror symmetry, where A side is a symplectic toric Calabi-Yau 3 manifold of 3 orbifold. And the B side is Hori-Vafa mirror, but then by the remodeling conjecture, right, so the remodeling conjecture tells us the B model can be reduced to this theory on the mirror curve. And on the mirror curve, the higher genus B model is mathematically defined by the Chekhov, the topological recursion. Right. So now we are going to, today we will provide details of this the statement and outline the proof. Yeah, so we start with the geometry of the A side. So let's C star P. So let GC be this complex algebraic torus of some dimension P. Act on P plus one dimensional complex vector space linearly and faithfully. Well, explicitly, we may assume like it's like diagonalized. So lambda acts on CP plus 3 by P plus 3 characters of GC. And so we want the quotient to be Calabi-Yau, so they should satisfy the Calabi-Yau condition. Essentially, it should preserve. Yeah, the action should preserve the holomorphic volume form on CP plus 3. So, but on the A model, we want to have the symplectic structure. So recall that Gromov-Witten invariants are defined for compact Taylor manifolds. So observe that the action of this complex algebraic torus restrict to a Hamiltonian action by the maxima compact subgroup. And so this Hamiltonian action with respect to the standard symplectic structure on CP plus 3. So this symplectic form. And then more explicitly, so each character can be written in this form. It's a monomial in the lambda I. So the power QIA are sometimes called the gauge charges, and they are integers. So they are weights of the torus action on the ice coordinate of CP plus 3. And so we know that the moment map is defined up to a constant. So up to a constant, the moment map of this compact torus action on CP plus 3 is, since we have the weight, it's just given by this. Very explicit. And if we suppose that we have a regular value, then in the best case, the compact compact torus G acts freely on this pre-image of this regular value, and you just get a Kähler manifold, and this sigma gives you the Kähler structure depends on this zeta in RP. And more generally, it will be a toric-Claviel 3 orbitals, and the Kähler form omega zeta is determined by zeta. Yeah, so we consider, so in the orbifold case, we consider the coarse moduli space is the GIT quotient. And this is a simplicial toric-Claviel threefold. So if the G action is actually free, then so we use curly X to denote the stack quotient, and straight X is the GIT quotient. Of course, when the G action is free, then these two are equal. In general, the straight zeta is a simplicial toric-Claviel threefold. So this is the A model geometry. Maybe let me do a very simple example. So suppose that GC is just one-dimensional C star. The maxima compact group is just a circle U1. So this is P is equal to 1. And the actions given explicit. So now we want the quotient to be three-dimensional, right? So if our torus is of dimension P and the vector space of dimension P plus 3. Now P is 1. Let lambda act on, let C star act on C4 by weight 1, 1, 1 minus 3. So this is, satisfies the Claviel condition. And then since the weight is given by this, and then the moment map of the U1 action is given explicit by this. So we see that when zeta is greater than 0, then Z1, Z2, Z3 cannot be O0. So the stability condition is Z1, Z2, Z3 cannot be O0. And the C star action, so when zeta is positive, it's free, and the quotient is the total space of O minus 3 over P2, the canonical line bundle over P2. So now suppose then 0 is not a regular value. So now let's take zeta to be less than 0. Then you see that the condition becomes Z4 cannot be 0. And then you can use the C star action to like move Z4 to 1, but this you still have leftover mu3. So here in this talk, mu m will denote the group of m's roots of unity. So now yes, so let curly x plus minus be curly plus minus 1, and straight plus minus be the coarse moduli space. So the curly, so when you see when, so for when in the positive phase, so this is just equal, and it's a symplectic toric-Claviel 3 manifold. In the negative phase, the stack quotient we take it's just the quotient of C3 by mu3, and this is an example of symplectic toric-Claviel 3 orbifold, and its coarse moduli space is a simplicial toric-Claviel 3-fold. Yeah, and in this case, actually, like KP2 and C3 mu3 are two different resolution. So KP2, so if you blow up the origin of C3 mod mu3, you get KP2, and this is a Torrey-Krepin resolution. And on the other hand, if you consider the quotient stack of C3 mod mu3, it is as smooth as a stack. Okay, so this is the example. So next we want to talk about the Chen-Ran orbifold cohomology. So recall that in Gromov-Witten theory, so we pull back classes from the cohomology of the target. It turns out that in orbifold Gromov-Witten theory, we need to replace that by Chen-Ran orbifold cohomology. So let U to oh, sorry. So this is a typo. So let X be so it's a symplectic quotient, and then as a complex or GIT quotient is by like U quotient by the complex algebraic torus. So U is the semi-stable locus determined by the stability condition zeta, which is a point in the zeta can be viewed as a point in the dual of the Lie algebra of the compact torus G. So now we fix this stability condition zeta or Kähler parameter, and we like just suppress that. So now this curly X is the quotient of U by the complex torus GC action. So there's a definition of inertia stack for general stacks, but now since our curly X is a global quotient by an abelian group, so we can just write down it more explicitly. So you take the point a pair ZB in U cross GC such that Z is fixed by the element B, or equivalent B is a stabilizer of Z, and then quotient by the action of GC. So when it's abelian, in the abelian case, so the action is given by just it acts on the first factor as usual, and the second factor trivially. And now it turns out that there's only because of the condition that there's only finite stabilizer. So it turns out that if you look at the group element where the group element such that it has a non-empty fixed point in U, the semi-stable locus, there are only finitely many of them. In particular, if the action is free, then this big capital B is the set of elements in the group GC such that the fixed point is non-empty. So this is a finite subset of G, and in particular, when the action on U, when GC action on U is free, so B consists of only the identity element. So in general, it can have like more, but it's still finite. So let X0 be, so the component. So we can rewrite it as follows. So we can rewrite this as a union of so it's actually a union of disconnected component indexed by the element in B. Sometimes it's also called box. Yeah, actually it corresponds to something called box, but let's call big capital B. Yeah, so there's a distinguished component correspond to the identity. So the fixed point of the identity is the whole thing. So X sub zero, yeah, is isomorphic to the original stack orbifold. And then you have the other component are usually called twisted sectors. Okay. Yeah, so so you see that if GC acts freely, then we only have the untwisted sector. And in this case, curly X is X, and the inertia stack is equal to itself. In general, if you have a point in like curly XB, so each curly XB, so it's a closed substack of curly X, right? Because it's a fixed, so the action, yeah, it's a closed substack. And also because B is the automorphism of every point in X. So the automorphism at the stacky point acts on the tangent space at that point. And since like B has like finite order, so it acts with eigenvalues, which are roots of unity. And then we can so epsilon I, we can choose unique epsilon I by requiring that it's greater or equal to 0 and less than 1. So we also know that because of the Calabi-Yau condition, when we multiply the 3 eigenvalues, we get 1. So the sum of E1, E2, the sum of epsilon 1, epsilon 2, and epsilon 3 is an integer, so it can be only 0, 1, and 2. So there's like a definition of age for like more general orbifolds. Yeah, but we are dealing with toric Calabi-Yau 3 orbifold. So the age can be only 0, 1, and 2. In the general case, the age can be fractional. I will define Chen-Rang orbifold cohomology of our toric Calabi-Yau 3 orbifold as a graded vector space over C. So there's a cup product, but this doesn't enter our definitions of Gromov-Witten invariance. Let's see. Right. So so it's just like it's essentially so we because we want to do mirror symmetry, so we will work over complex numbers. So now all the cohomology has like coefficient in it, the coefficients are complex, it's the field of complex numbers. So they are all like complex vector spaces. So if you just consider it as a C vector space, then the Chen-Rang cohomology is the same as the cohomology of its inertia stack. And inertia stack is like disjoint union of XB. But then the grading is different. So if so we just define this age. So we know the age can be 0, 1, or 2, and we need to shift it. So for x0, we don't shift it. But if you have B, which is of degree 1, so H can be degree 0, 1, or 2. So if you have H1 element in the box, we call capital B the box, then so we shift it by 2. And as we so then we see that this is so yeah, so the degree zero part is like 1, 0, correspond to the unit of the untwisted sector. Yeah, so this is, oh, and also there's so let G hat be the dimension of dimension of H forced cohomology, forced chain-run cohomology. And it turns out that the P will actually be equal to the second chain-run cohomology. Yeah, so let me do this example. So for example, if we take C3 mod mu3, so here, oh, I should say that, yeah, so we now use it's easier in this case to use just the, yeah, just a discrete group mu3. And so then the inertia stack, now this inertia stack, so you see that mu3 like has like identity fix everything, and the other two element fixes the origin. So the inertia stack, so in this case, capital B is mu3, and the inertia stack consists of 3 connected components. X0 is X, and the other two components are so just the origin quotient by mu3. So it's classifying space of mu3. And the H, because zeta, like zeta, so here, oh, this is not a very good notation, sorry. So because yeah, I hope it's okay, because at some point I use zeta as the Kähler parameter. So maybe let me make it Cauchy. Yeah, so we see that because the like Cauchy acts by, yeah, then if we follow the definition of the H, the epsilon, epsilon2, and epsilon3 for Cauchy is like 1/3, 1/3, and 1/3. So the H of Cauchy is 1, the H of Cauchy squared is 2. And then, but the cohomology of each component in this in this example is just H0. So yeah, so we have just the unit of the cohomology, but for the twisted sector, we need to shift by the degree by 2 or 4. And so let's see. So also we know that so if we consider the quotient of C3 mu3, and we can resolve it by blowing up the origin, we get a Torrey-Krepin resolution KP2. And KP2 is smooth, so it's just the cohomology is the same as KP2, and also KP2 is a deformation retract to its 0 section. So it's the same as the cohomology of P2. And so at least for now, we see that these two are isomorphic as a graded vector space. But actually it's in general true. So if you have a Torrey-Calabi threefold, which is a Torrey-Krepin resolution of some Torrey-Calabi of the coarse moduli of some Torrey-Calabi 3 orbifolds, then their chain-run cohomology are isomorphic as gradient vector space. But the chain-run cup product, which we are not going to use, they are not isomorphic. But then so So, but as graded vector spaces, they are isomorphic in general. Okay, so that's the geometry and topology on the A model. Okay, oh, sorry, I see. Oh, I see. So now we will talk about A model topological closed rings. So they are Gromov-Witten invariants. But now we are going to do orbifold Gromov-Witten invariants. And we'll also do the equivalent version because toric Calabi-Yau 3 orbifolds are non-compact. So first, let's given, yeah, it's similar, but there's some modification. So again, we want to fix some non-negative integer G and N. G will be genus, N will be the number of mark points. And we fix some effective curve class in, say, the force moduli X. So this M bar G and X beta is the moduli space of genus G M pointed degree beta twisted stable maps. So what do we mean by twisted stable map? First, since the target is now it's an orbifold, so we want to allow the domain to have orbifold points, but we only allow orbifold points at the mark points or at the nodes. The other points are scheme points. And so we also require this, then now you have like a morphism from an orbit curve to our toric Calabi-Yau 3 orbifolds. So we require this map is representable. That means if you have an orbifold point and you map to another point in the target, then it induces map between automorphism group, and we require that this map is an injective group homomorphism. And also, so you have this nodal orbifold curve, possibly nodal orbifold curve, and you can consider the coarse curve. It's just you forget the orbifold structure at the mark point and at the nodes. And then this coarse curve will be a genus GM pointed pre-stable curve. And the map to the coarse curve will be isomorphism away from nodes and markings. And also, we also require at the nodes, it's locally isomorphic to like the origin in here, but it can be stacky with some cyclic automorphism group. But the action on the two branches, X and Y, must be opposite. Okay, so that's the definition of that's an analog of moduli of stable maps, but now it's like twisted stable maps. Oh, so now, also there's something that we need to, so over the moduli space, so this mark point forms some gerb, we want to trivialize it. And then if we do that, so we will have this evaluation map, but the evaluation map now will take values in the inertia stack. So let me see. So if you are given this twisted stable map, which is like this orbit curve with nodes, possibly with nodes and with mark points, and some morphism from this orbit curve to the orbifold curly X. So we send it to xj zeta. So then you will get a point in X together with an automorphism of that point, which is exactly a point in the inertia stack. So let me see, what is this? Yeah, this is bad. Let me say this is zeta. So if your if your point xj is actually a scheme point, then I mean then the automorphism is like the identity. And then this map will be so if your xj is not an orbital point, it's a scheme point, then the image is in the untwisted sector. But if it's but suppose that your xj is a stacky point. Oh, I think there's some overlap for some reason. Okay, so you see so if your xj is like b mu rj, so the automorphism group is a cyclic group of some order rj. So we pick a generator such that this generator acts on the tangent line of xj by exponential. Okay, so yeah, so you see like there are like different choices. Yeah, because for if we think it additively, like we can pick anything which is co-prime. So this is like, yeah, so we can, so anything which is co-prime to RJ can be a generator, but we need to specify a particular generator characterized by so x the tangent line for the orbital curve by this weight. Yeah, so this xj together with Cassie will be a point in the inertia stack of the domain orbital curve. So yeah, so the evaluation map lies in the in the inertia stack. So yeah, so so recall that to define like a general descendant Gromov-Witten invariance, we need to introduce moduli of stable maps. So now we have introduced moduli space of three stable maps. We also need to use evaluation map and also Passaic classes. So now we have explained the evaluation map. So next is so the Passaic class, we consider the line bundle is actually the cotangent line of the coarse curve. So so it's like some power of the cotangent line of the orbit curve. Yeah, it's just behaves better if we use this. So the Passaic class, we call it Passaic J hat, is the C1 of this LJ. So it's like cotangent line of the coarse curve. Oh, okay. So now also you see that yeah. So we have so this tori Clavius-3 orbifold has the action of C star 3, just like the tori Clavius-3 manifold, and also we also have a Clavius torus. And then all this evaluation map is equivariant, actually T equivariant, and in particular T prime equivariant. So we are going to use the, so as we did in the topological vertex, we are going to just use the Flabial subtorus. And as a C vector space, so the T prime equivalent Chen-Ran cohomology is just T prime equivalent Chen-Ran cohomology of the inertia stack. So this is a direct sum. But then we need to, but then as a graded vector space, we need to shift the twisted sectors by twice of the age. So now given this, so the state space is now like equivalent Chen-Ran cohomology of the orbifold, toric labial 3 orbifold. And to define descendants, so we take gamma 1 to gamma n in this T equivalent Chen-Ran cohomology, and we take A1 to AN, which are non-negative integers. So yeah, okay, so since it's defined by psi hat, let me put tau hat. Yeah, so we define it by this localization formula. So T prime, yeah, so this is like defined by the localization formula. So it's in general some rational function in the equivariant parameter U1 and U2. So sometimes later we will see that we will sometimes even specify to a one-dimensional subtorus called the framing torus. So this framing torus is actually determined. So recall that we have a like when we define open Gromov-Witten invariance, counting holomorphic curves with boundary in a Lagrangian, we need to specify a framing. Yeah, so that framing will actually determine a one-dimensional subtorus. Yeah, it's embedded in this way with some specific choice of the coordinates on the Calabi-Yau torus T prime. And then, so then we know the so recall the equivariant cohomology of BT prime is a polynomial ring in two variables, U1 and U2. And then the inclusion of this one-dimensional subtorus, yeah, so induces a map between equivariant cohomology of a point explicitly given by this. So if we have any correlator, so when we write T prime, it's T prime equivariant. And when we write TF, it's like restrict to the framing torus. Okay, so now let tau be a second cohomology class. So this is like the extended Kähler parameter. So we have, so this is a single correlator. It's like, and for double correlator is in addition to this insertion, we insert any like all the possible, like any number of tau L. So this will make this correlator depending on tau. So it will depend on p variables if we choose some coordinates. Oh, I should say the following. So actually, more explicitly, so we have this non-equivalent Chen-Ran cohomology, and yeah, it's like p-dimensional. So we have some specific way to choose a T prime equivalent lift based on the position of our Lagrangian. Yeah, so we have this double correlator. It will depend on this extended Kähler parameters. Yeah, so you see that, like, for example, like if you consider C3 mod mu3, so I mean it has no actual H2, right? So I mean the Kähler parameter is 0, but but we need to consider like the stringy Kähler moduli or extended Kähler moduli. So if we consider Chen-Ran cohomology, then the second Chen-Ran cohomology of C3 mod Z3 is one-dimensional. Yeah, so it behaves well under the Krepin transformation. So we have this, so these are like equivariant close descendant Gromov-Witten invariants. And actually, so it will be convenient, as we see later, to use another way to package the descendant Gromov-Witten invariants, is write it as like the last line is like this double correlate gamma 1 over Z1 minus psi 1. Okay, I should actually write hat. So this is you formally expand it by power series and then and replace, yeah, so you just formally expand it by power series, and so yeah, it's an infinite sum. So the power of Zj will oh yeah, actually, so this should be minus, yeah, if we expand, right? Because like if we expand this, so this is okay, so finally, so let's look at the so in particular, this we can consider so you see this double bracket, it already sum over all the possible curve class and all the possible number of tau insertions. So now suppose that we can consider this double correlator without any, when n is 0, then then we don't insert anything. But we don't insert anything, but because it's double bracket, so we can this include insertion of any numbers of tau. So it still depends on tau. So this should be the yeah, this should be the G Gromov-Witten potential in the orbital case. Okay, so oh yeah, so this just remark that the divisor equation in the orbital case only works on the H2 of untwisted sector. So you can divide, you can only, yeah, this is, so the degree to the divisor. So recall that in Gromov-Witten theory, there's a divisor equation for degree 2 element. So now in orbital Gromov-Witten theory, that divisor equation only works for the element in the untwisted H2. So on untwisted H2, yeah, so this is, we can like apply the divisor equation. So we can apply the divisor equation and then so remove all the insertion. Then yeah, this reduces to our definition in the smooth case. Okay, and any questions? So these are the close equivariant descendant invariant and also the genus G Gromov-Witten potential. So next I want to talk about open Gromov-Witten invariants. So now we are in an orbifold. So recall that we write X. So we want to specify the orbifold version of this Abnagich Vafa Lagrangian brane. So we write our toric Clavius 3 orbifold as a symplectic quotient. And so then we want to write this Lagrangian. Also, we actually first specify some L tilde before the quotient. And it's actually quite easy. They will just be defined by yeah, so we specify like three real conditions. So these are the three real conditions. So this will, so before the quotient, it will be real codimension 3. And then this will actually be, it will actually be after the quotient, it will be Lagrangian in the sense that it's a three-dimensional, but in this case, it's three-dimensional submanifold or suborbifold, and such that this symplectic form restrict to 0 on this curly L. So in general, because this L will intersect a unique one-dimensional orbit. But now the one-dimensional orbit in the orbifold case, it can be like, yeah, it can be, this one-dimensional orbit can be like C star B mu M. And if you take the closure, it will be like, the closure will be C times C quotient by, oh, sorry. Yeah, let me, the stabilizer at this fixed point can be larger, but the orbit, yeah, it's one-dimensional. The orbit doesn't include this, but in general, the one-dimensional orbit can have a sorry. Yeah, so I want to say that in the original paper by Fecha, Clem, Marino, and Pascali, so when they do the orbifold case, they still want L to intersect just a copy of C star. But we can allow this. So our L looks like, so our L is actually, yeah, it's topologically some line bundle over. So this, yeah, you can think this as like a total space of a real vector bundle of rank 2 over this circle times B mu M. Okay, so now I want to define open Gromov-Witten invariance for such a pair. So they are virtual counts of holomorphic map from border Riemann surface. But now, similarly, we need to allow our border Riemann surface to have orbifold points at the mark. We need to allow our border Riemann surface to have some nodes and also mark points. So in our set, to define our invariance, we don't put mark points on the boundary. So all the mark points are in the interior. So we only allow stack key points at the nodes, and at nodes again, we require this balance condition, and it can have so the mark points can be stack key, but otherwise other points are scheme points. So it's a border Riemann surface with possibly stacky mark point and possibly stacky nodes. And each boundary circle are like connected, boundary circle is yeah, so the boundary is a union of, yeah, a union of circles and circles. So what does this invariant, okay, let me see. Or maybe let me do this, sorry. Okay, yeah, so now we have a picture. So first look at the picture on the lower part of this page. So you see the domain is like Riemann surface. No, so I draw some smooth domain. Smooth in the same sense of orbifold. And then, but it can, but the mark point can be orbifold, so it's like some, it looks like a cone. And then we also have boundaries. So boundary circles R1 to Rn, and the interior mark points X1 to XL. So we consider holomorphic map from this domain to the target such that the boundary circles are mapped to curly L. So today, like, we will only put one Lagrangian boundary condition. So then there's only one partition, and the component of a partition, yeah, so tells us the winding numbers. Yeah, okay, so let's see. So let me just start from the first item of this page. So this invariant should be depend on the topological type of the coarse moduli of the domain. Yeah, so the domain is just a border Riemann surface of genus G and N whole. So it's depend on G and N. And we also specify the topological type of the map. So now the degree is like becomes a relative second homology class. And we also have winding numbers, but yeah, because of the orbifold structure. So suppose that our L is actually just a manifold. The Lagrangian is a manifold as circle times R2, and it's let's say it's pi1 is just Z. So then you only need to specify. So then this so if you restrict the map U to the circle Rj, it represents an element in pi1 of L. So when it is smooth, it's just an integer. And yeah, so it's called the winding number. So, but suppose now that RL is now contains stacky points, and we have explained that this L in general is homotopic to it's a rank 2 vector bond over a circle times B mu M. So it's homotopic to circle times B mu M. And the pi1 of a circle times B mu M is Z cross mu M. So this circle, yes. So now now we need to keep track of the winding number and also the mu M monodromy. So Ki is an element in mu M, or we can also think it as like in the additive version of mu M. So Z mod Zm. Okay, so you see that then we need to specify the number of, yeah, we specify Gn. Yeah, so you see we need to specify Gn, which, so G tells us a genus, N tells us how many boundary circles are there, L tells us how many interior mark points are there, and B prime is a relative homology class. It's a degree in the open Gromov-Witten theory. And now this mu is it's an N tuple, where each tuple consisting of a winding number and a monodromy associated to the the ice component Ri of the boundary. So yeah, this is kind of long, so let's introduce the some shorter notation since we are fixing X and L, this omit X and L. And also the number N is determined by the number of components of this mu. So we don't need to specify N. So it's like G, L, yeah, so let's code. So you see when we fix all this topological type of domain and the map, so we have this, yeah, so we have this moduli space. Right, and now, so this moduli space doesn't, so we know that, yeah, so the invariance will also depend on a framing of the agnetic Vafa Lagrangian brane. So the framing is enters when we define the invariance. So the moduli space only depend on 1 and 2. Okay, so now similarly we okay, so I think I can yeah, so oh boy, so so yeah, so similarly we can take we can consider evaluation map at ith interior Mar point. So it takes values in the inertia stack. So now we can use this moduli space of yes, like stable map, like stable maps with Lagrangian boundary conditions to define open Gromov-Witten invariance for this toric-Calabi-Yau 3 orbifold as follows. So these are like primary invariants. So we don't, yeah, so we just pull back this T prime equivalent Chen-Ran cohomology, and we can, it turns out if you use local, it turns out that if you can, so, oh, okay, so first of all, these Lagrangians are not preserved by the Calabi-Yau torus, but they are preserved by the compact Calabi-Yau torus. So this compact Calabi-Yau torus acts on this moduli space of, yeah, moduli spaces of holomorphic maps bounded by the Lagrangian. And then we just do, like, we can compute it, yeah, we can compute this by, we define it by localization. Yeah, the subtlety is like this moduli space is in general not complex and does not have a canonical orientation. But because, yeah, actually we can similarly define the relative version as we did last time. So actually we have like can generalize the definition in terms of relative Gromov-Witten invariance to the orbifold case. And then because like the moduli of relative stable maps is complex, so this gives us some orientation. Okay, so we have some way to orient it. And also, so the framing says that we first do localization using this two-dimensional compact torus, and then we restrict to this one-dimensional torus. So that's like you specialize the weights U1, the U1 to U and U2 to FU, where F is the framing. And we need to choose a generic framing or good framing such that when you do this specialization, you don't get poles because, yeah, in general, it's a rational function. You want to make sure when you do this, yeah, you don't have poles. So yeah, okay, so I will take a break after this slides, after finishing this slides. Yes. So the generic framing, like geometrically, just means that if you consider the tangent weights to the invariant P1s at the fixed point, you want to make sure that when you restrict to this one-dimensional framing torus, all the weights are not zero. So that's a good choice of framing. And also, so these are like a open Gromov-Witten invariants. And then finally, we want to form a generating function. So we want to insert degree 2 classes. And then, so this is a generating function. So we insert any possible number of tau degree 2 classes. So we sum over all degree, and we sum over all the winding numbers. So the winding numbers. So the winding numbers are keep tracked by the xj tilde, and then the monodromy are keep tracked by some. Yeah, so we want to keep track of the monodromy. So this generating function is actually a vector valued function. It takes values in the nth tensor product of the chain-rank cohomology of BZM. So the inertia stack of BZM consists of M connected components, all isomorphic to BZM. So the chain-rank cohomology of BZM is M dimensional. Yeah, so one for each one untwisted sector. So yeah, so let one prime km denote the unit on the component associated to like the element k in Z mod M. So we define this. Okay, so now we have defined the A model. Yeah, we have rigorously defined the A model topological strings or toric Flabial 3 orbitals. So I think maybe it's time to take a break, 5 minutes break. Yeah, so we have this generating function. Yeah, so you see there's this Q here. So the Q is some novical variable because a priori we don't know if this series converges. But actually, yeah, so we will let it to be 1, and for now it's some formal series as follows. So you have this tau 1 to tau p prime plus 1 to tau p. So these are the parameters associated to hx, the untwisted sector, which we assume is like some p prime. So if you are in the smooth case, p prime is equal to p. And we know that, so then this will depend on e tau 1 to e tau p prime, and tau p prime plus 1 to tau p. So right now we can view them as like formal power series of these variables. And then we see that the first p prime variable will keep track of the degree already. So we don't really need this additional parameter q, and we will set it to be 1. So now it really only depends on we will say the A model closed string parameters from tau 1 to tau p. And open string parameters is x1 tilde to xn tilde. Okay, so now we have defined the generating function of open Gromov-Witten invariance and the generating function of a closed Gromov-Witten invariance, depending only on tau. And we also have some generating function of closed descendant Gromov-Witten invariance. So here is the theorem is the following. So there's a statement. So for simplicity, we assume 2g minus 2 plus n is greater than 0. And actually in this case, for each gn, there is a decorated stable graph, which can be, you take the dual graph of m bar gn and add some additional decoration. But in any case, this will be a finite sum, a finite set. And So it turns out that this open Gromov-Witten invariance can be written as a sum over graphs. And also when when G is greater than 1, the closed Gromov-Witten invariance. So we can like, to unify the notation, we can say like G0, because you see like if you, yeah, so if you take the, oh yeah, so this just means there's no boundary, so your boundary cannot go to the left. Yeah, there's no boundary, so these are closed invariants. And so open invariant depend on the like tau and tau 1 to tau p, and also x1 tilde to xn tilde, 1 for each boundary component. So when n is 0, so yeah, it doesn't depend on the xi tilde. And also, so for the descendant invariant, it will be convenient to organize it in the following way. So to introduce extra variables z1 to zn. So now suppose that we insert gamma 1 to gamma n, and then we can also write it as a graph sum. So basically, yeah, so actually this two, you will have the same set of graph. It's just for different invariants, the weight of each graph are different. Yeah, actually more precisely, so this is like a model. Yeah, so let me maybe write, yeah, maybe I call this Z and this Z because there's some dependence on Z. And so for the A model, like graph sum and the weight of like for the open Gromov-Witten invariance, yeah, which also include this FG, like the primary closed Gromov-Witten invariance. So it's a contribution from vertices and edges. They only depend on closed string parameters tau. And also there's some dilaton leaf also depend on like a closed string parameter. But the open leaf, so in the open case, we have open. So you see the weight, the difference of weight is of these two cases, the open case and the descendant case are the following. So first, for the open case, we use the smaller torus, the framing torus, and the invariant will depend on the framing. And yeah, but then otherwise, the weight of the vertices and the weight of edges and the weight of like so-called dilaton leaves, yeah, are essentially the same up to this restriction to the framing torus. And they only depend on the closed string parameters. And but for the leaves, so the open leaf will, so for each J, the open leaf, so the J's open leaf, so depends on the tau and also xj tilde. So the open string parameter correspond to the J's component of the boundary. And this, so let's say the descendant leaf depends on tau and zj, and also the insertion gamma j at the J smart points. So to prove the formula, so the proof is like summarized by yeah, we do localization, and also so given tau has a formula for all genus full descendant potential for equivariant Gromov-Witten theory of toric manifolds. Also, there's some unfinished book by Lee and Panda on like given tau's proof in the manifold case. But now given tau and Xianhua Zeng and Tom Coase, they have some formula for toric bundle So some fiber bundle whose fibers are toric manifolds. So in any case, those cover the toric manifold case. And Genu's thesis, yeah, in 2000, he finished it. He defended it about 10 years ago. So he generalized this to to the orbifold case. Yeah, actually, what he did is in the thesis is like more general target with torus action, such that the fixed points are finite and the one-dimensional orbits are finite, and with some additional conditions. So in particular, it doesn't need to be toric. And and also like given Tau's quantization formula should also hold for that setting. So this is much more general, and it doesn't have restriction on dimension. It doesn't need to be actually toric, as long as you have like finally many fixed point and fixed and one-dimensional orbit. Yes. So using that, using this localization zone thesis, so we can prove this A model graph sum formula. So the proof will actually be the following. So next we are going to define B model topological strings. And then there will be B model graph sum formula for the B model topological string. And then the graph sum formula will be like sum over the same set of graphs. So we need to, the proof is that we see that the contribution for each graph is the same, like on the A model and B model. So that's the preview of the proof. But now let's define, so we have finished the A model geometry and A model definition of A model topological string, and also graph sum formula, which is a key ingredient of the proof. So now we will talk about B model geometry. We will define, we will define B model topological string. So recall that the mirror curve is it's a fine curve in C star 2. And this depends on the your given toric labial 3 orbifold. So actually this is determined by, you take the underlying, like the coarse moduli space. It's a toric labial 3-fold, with some orbifold singularity. So it defined by a simplicial fan. So in general, toric varieties are defined by fan. So the fan is in, but in this case it's easier. Let me just say the following. So in this case, so the fan is in it is in the Lie algebra of the compact labial torus, which is like R2 times R. And the labial condition tells us, so if you take the support of the support of this simplicial fan is a cone over it's a cone over a two-dimensional thing in R2 times 1. But now we also have the condition that this comes from a GIT quotient or symplectic quotient. That will imply that this is a cone over a convex polytope. It's the convex hull of some lattice points n in R2. So then then we have, so I will, next page there will be some examples and pictures. So for each toric labial 3 orbifold, and so you take the fan, the support of fan is actually cone over some polytope. So this polytope in R2, and then this polytope is the Newton polytope of this equation define the mirror curve. So the coefficient will depend on, so the complex parameter, yes, in one-to-one correspondence with the, as we will see, with the Kähler parameter, extended Kähler parameter on the A side. So now this, so there's a polytope, So basically you consider this fan, the three-dimensional, the one-dimensional cone are like rays will intersect this polytope at points. So and the two-dimensional cones will intersect this polytope along edges, and the three-dimensional cone will intersect this polytope in triangles. So basically, so if you intersect this fan with this cone at level 1, you will get a triangulation of this polytope whose vertices correspond to T divisors, edges correspond to T curves, P1s or more P1s or projective lines or complex projective lines or complex lines, and faces correspond to the torus fixed point. So the torus fixed points can, if you look at the orbifold, in the orbifold they are possibly stacky points. So here are some combinatorics. So this polytope, if you take the interior lattice point, we call G hat the number of interior lattice point. They will actually coincide with the fourth Chen-Ran cohomology of the original toric labial threefold. Let n hat be the number of boundary lattice point. And then it turns out the second Chen-Ran cohomology is equal to the number of the lattice points in the polytope, including interior and boundary, minus 3. So it's G hat plus n hat minus 3. So you can think so minus 3. So you see, like, roughly speaking, you look at the coefficient, it should depend on P plus 3. But then there's some, but then this is not the actual moduli, right? Because if you like change it by an overall scalar, it won't change the zero locus. And also you can reparameterize your torus. So roughly speaking, so that's why the complex moduli should be the number of terms, which is equal to G hat plus n hat minus and minus 3. So now let's see. So the dimension of the Chen-Ran cohomology is like, so H0 is one-dimensional, H2 is p-dimensional, and H4 is G hat dimensional. It's 2 G hat minus 2 plus n hat. It's equal to the negative for the Euler characteristic of the mirror curve. Indeed, the mirror curve has G hat and n hat punctures. Okay, so this is so now maybe it's better to So let's look at this picture, then it will be clearer. So first of all, because we are doing, so we now assume it's an like honest symplectic toric labial threefold. So then recall that when we did the topological vertex, we used the configurations. So we use this configuration of curves in the one skeleton to draw this toric graph. But now actually what we can do is the following. So we take the, on X, there's an action of the three-dimensional compact torus. So there's a moment map. And under our condition, the image of the moment map will be a convex polyhedra. It's not a complex polytope because it's unbounded. So if we use a three-dimensional, because now let's say curly X, so yeah, so actually this I should write curly X. Right, so this is a Kähler orbifold. And then the compact three torus, so we have this TR, so it's compact three torus, which is in our T. So it's a Hamiltonian group action. The moment map, yeah, takes values in R3, and the image is a complex polyhedra. So now when we restrict to the Calabi-Yau two-dimensional compact Calabi-Yau torus, yeah, then the image is actually becomes, so this is essentially you project this moment polytope, moment polyhedra, because it's unbounded. So we project this moment polyhedra to the two plane. And then you look at the image of the one skeleton, you get a toric graph. So the symplectic condition will take you, so now you will actually get not a locally planar trivalent graph. You will get an honest planar trivalent graph. So if you restricted this to the one skeleton, this is still an embedding. It cannot intersect. The edges will not intersect. So if we do OP1 minus 1 plus OP1 minus 1, recall we get this. And also now, because we, so now also now the edges is not only abstract, it has a length. And the length correspond to, so you see that in this case, in the resolved conical O minus 1 plus O minus 1 over P1, it's smooth and it's just Kähler module is one-dimensional. It's determined by the symplectic area of the zero section. And the symplectic area of the zero section is proportional to the length of this closed interval, which is the image of the zero section P1. So this graph actually also depends on the symplectic structure. And also now, if you look at the cone picture, is basically the due of the FEM picture. So here the polytope is this the polytope in the resolved conical is given by this, and so you see that it has 4 boundary lattice point and no interior lattice point. And the mirror curve is you just take the toric graph and fatten it. So you get, basically a sphere with 2 punctures. So you see like the number of punctures is equal to the number of boundary points with boundary lattice point of the polytope, which is 4. And the genus is 0. So now let's look at local P2, O minus 3 over P2. And we have wrote that. So now using like this moment, so we can obtain this graph by using the moment map of the compact Calabi-Yau torus. And we see that we have a triangle, which is the image of, the triangle is the image of zero section P2. And also the Kähler modular P2 is also one-dimensional. And it's given by, the size of a P1, the symplectic area of this a P1 in the zero section. So the larger, so it's given by the size of this triangle. And dually, so the fan picture, if you intersect fan over the level 1 hyperplane, you get this dual picture. So now you see that the polytope in this case is triangle. It has one interior lattice point, and so this is, I think, yes. So this is 0, 0. You see it has one interior lattice point and 3 boundary lattice point. The mirror curve, so you really write down the mirror curve. And for generic Q, the mirror curve is smooth. And it's genus 1 with 3 punctures. And actually, if you go to the C3 mod mu3, what happens is then you now shrink, you now make this scalar curve goes to 0. So at the end, your P2 is shrink to a point, and you get C3 mod mu3. Yeah, so in order to continue to the other direction, we have this extended scalar parameter. So which allows us to go to the, yeah, and we will complexify it. So this allows us to continue. And then, so the mirror curve topologically still is like, genus 1 with 3 punctures. And finally, so that we have this polytope. So so this is really, the topological type of the mirror curve in general. So so we let G hat and be the number of, be the genus of, because in the topological recursion, we have G and N, right? So, but now for this mirror curve, there's a fixed G hat for the genus of the mirror curve, and fixed N hat, which is the number of punctures. So this polytope, this two-dimensional polytope actually define a toric surface together with a polarization L. This toric surface in general can have orbital singularities. For example, if you start with OP2 -3, then this polytope will actually give you the toric surface is P2 mod mu3. Yeah, so that's why, like, then this so then this H, so here CQ is the H, X, Y, Q is equal to 0. So this is also, this also depends on some. Yeah, but this extend to the boundary, and extend to the boundary, and it becomes a section of this line bundle. And the compatified mirror curve is obtained by like adding the so the compatified mirror, so the punctures of CQ will become the mark point on C bar Q. So compatified mirror curve has genus G hat. Okay, so now that's the geometry and topology of the B model mirror curve. So now in order to define, so now we will define like Chekhov-Aina-Arnton topological recursion. This will allow us to define B model topological string. So let little x be minus log x, little y be minus log y, and x hat be u1 x plus u2 y, and y hat. And so this is this is when we do descendant, we want to do this. But when we do the open, we want to do this. So this is descendant. So maybe let me say that if we do the open, we want to do x plus y, and y hat is y, and then we have this axis will be, oh, yf, yes. So the initial data is like a one form y hat dx. Oh, so yeah, there's some, so this y hat is multi-value, but this is fine. So omega 02 is so you should think omega 01 associated to the disk, right? So it's G 01 boundary, and omega 02 will give us annulus invariant G 02 boundary components, and omega 02 is the so-called, is a classical object, I think known by Riemann. It's fundamental normalized bidifferential of the second kind on the compactified mirror curve. So I'll call it C star. And it's characterized by the following properties. So first is bilinear symmetric meromorphic differential on C bar cross C bar. It has a double pole along the diagonal, and it's holomorphic away from the diagonal. So there's some normalization. First, the local normalization is the following. So in local holomorphic coordinates near a point PP in the diagonal, so we have holomorphic coordinates Z1 and Z2. So then we can write this in local coordinates near PP. So then the meromorphic part is given by 1 over Z1 minus Z2 squared. And this is the symmetric DZ1, symmetric tensor. Oh, sorry, I should say that this is DZ1, DZ2, but then it's symmetric. So this part is just a symmetric holomorphic function in local coordinates Z1, Z2, symmetry in Z1 and Z2. So by Cauchy integral formula, we see that if we take a local function, like holomorphic function defined near P, and we take the residue, so this is two form, and we take a residue with respect to the second part, and then we get a differential of f at P. Oh, so this is local normalization. It's locally, yeah, it looks like this. And there's a global normalization which is needed when your curve is of higher genus. Because you see, if you have some B which satisfies 1 and 2, and because on a higher genus curve, you have holomorphic 1 form, you can just take the tensor of like holomorphic 1 form and you add it to B. It won't change this, right? Because, yeah, they are holomorphic. So we need this global normalization. Is take any symplectic basis of the first homology of the, of the compactified mirror curve. And you require that if you integrate this BPQ, like you take the first factor and you integrate along the A cycle, we call alpha, and these are all 0, right? So this will exactly, so this is, so this normalization depends on our choice of symplectic basis. Actually, this only depends on choice of the span, because this condition is a span of alpha j. So it depends on a choice of like Lagrangian subspace. So in the original setup, so in the manifold case, so we can choose integral symplectic basis, but it turns out that if we want to do orbifold Gromov-Witten theory, So let me say that, so you see that we will define omega gn recursively, but these are the initial condition. If we change the initial condition, well, we will get different omega gn. So we have already used the geometrical mirror curve to give us like omega 0, 1. So to give us a mirror curve and omega 0, 1. So this we will also actually use the data of our A model to choose this symplectic basis. And so we need to make such a choice such that use this initial condition, we are going to match the Gromov-Witten invariance. And so we assume that this has simple poles. So you see that this X has log. So X is not a globally defined function, but dx hat is so you see that this is a nice holomorphic one form on C star times C star. So it restrict for each. So if you now view U1 and U2 are just like complex constants, and so for generic U1 and U2, so this has simple poles, and we view them as the critical point of X hat. And because yeah, right. What do so you can think it as follows. In the open case, it's like we have this mirror curve in C star 2, and then you C star, and this is given by so-called S hat, which is XYF. So C star is like Euler characteristic 0. So the number of, so we choose generic so that generic F such that this X hat is holomorphic verse. So it's a simple, all the branch points are simple. So then you should, so then the number of branch points will be equal to negative of the Euler characteristic of CQ. So now for each critical point alpha, so near this we have like 2 branches. So for each alpha, we have this recursion kernel, which constructs, so we have this fundamental bidifferential. So we take P1, and for the second argument, we integrate from P. So it's a 2 form, symmetric 2 form, but we integrate the second factor from like P to sigma alpha P. So this becomes a locally 1 form, and we divide it. So this will be locally looks like these. So this is the local recursion kernel. Yeah, I hope this is so this is defined. So what do I want to? Sorry. Oh yeah, so the recursion kernel, you see, like P1 can be any point, but P is a point near alpha. Okay, so this defines the recursion kernel. So if 2G minus, so now we have initial condition omega 0, 1 and omega 0, 2. We define the topological recursion is defined recursively as follows. So we define omega gn like using the residue and lower, so and the omega gn plus 1 m g minus 1 m plus 1, and also yeah, so there's another sum. So to remember the recursion, you take omega gn, and so consider, and you look at this P1, consider ways to remove apparel pairs with one boundary component P1. And this is the way to remember this like topological recursion. And the thing is the right-hand side, so this right-hand side involves like Gn such that like it will decrease 2G minus 2 plus n. So it's an induction on 2G minus 2 plus n. And when 2G minus 2 plus n is greater than 0, so you get some symmetric meromorphic form on the compactified mirror curve, which is holomorphic away from the critical point of x hat. So it's even holomorphic extended to the puncture. And moreover, so it's of the second kind in the following sense: if you take the residue and it's 0, so the pole, like it's like pole has no residue. So this defines omega gn, and omega g0 is obtained by further we define omega g1 and we take further residue, and this define omega g0. But after you take this further residue, this becomes a function depending on q, little q. So the B model FG is actually up to a sign as omega g0q. So now we can define B model topological open string. So it's all construct from this omega gn. So for the one, so for the like this invariant, basically we take the antiderivative of so recall that omega 01 is y dx. So but this has, so this is minus, this is log y. Yeah, up to some, but then the thing is now if you look at this form, so you look at, so if we consider the so a Lagrangian on a stacky, Lagrangian which contains stacky points, and then this will correspond to m punctures on the mirror curve. So now the map from mirror curve to the C star can be extended to a branch cover from the compactified mirror curve to P1. And then let's look at, so this 0 is not a ramification point after we extend it. So this holomorphic coordinate x hat near 0 on P1 are good holomorphic coordinates like on these punctures. So we can use this, so we can pull back. So but then now you see that it has a pole. So basically this is like remove the co of omega 01. And then we take antiderivative. And but then this we have like different ways because there are different pre-image. So we sum over them and it's vector valued. And to match the A model, it will be so the puncture, the bases correspond to the puncture. and the bases correspond to the A model differ by this, this change of bases. Yeah, so apparently I think I'm yeah, so maybe let me just finish this 2 slides and I'll stop. Yeah, so also annulus invariant is by so it's by like pulling back W2 and remove the pole part. And for the omega GN, then we just use this to pull back to the tensor product. So use for each choice of L1 to Ln, which are elements of mu m. Oh, so actually Li can be should be viewed as the dual of, so Li you should view it as the dual of mu m, and then we can. So after we pull this, and it will look, so after you do this, it will look like some like holomorphic thing, right? And then you take the antiderivative. So so these are the B model topological string defined. So we have defined omega GN, and we define precisely the B model closed and open topological string. So here is our theorem. So we have defined the A model topological open closed string and A model topological open string. They are related. They are related by this. So after we do this very explicit open and closed mirror map, so you see that the closed string parameter on the B side is like little q1 to little q, little q1 to little qp, and the open string, the closed string on the A side is tau1 to tau p. And so on the B side, the open string parameter are x1 hat to xn hat. The closed string, the open string parameter on the A side is x1 tilde to xn tilde. So we have this. So they are related by open closed mirror map. So which can be written down explicitly. So for the first P prime, so tau A is equal to log QA plus some holomorphic function in Q, which is 0 when Q is 0. And then we also have the parameter correspond to the twisted sector is tau A is like first order is QA. And we also have the quantum correction for, so for the open string parameters is for each J is given by the same quantum correction, which only depend on the closed string parameter. So this is our theorem. So this is proof and extend the original remodeling conjecture for toric Labial 3 orbifolds. So okay, so let me just say that the new result. So this is with Bo Hanfang and Zheng Yuzong. Bo Hanfang is at Peking University and Zheng Yu is at Tsinghua University. And like my last sentence is say that with joint with Yu, so it's a joint work in progress, is to get this descendant Gromov-Witten invariant. We actually take this omega GN and do this kind of oscillatory integral. And you see, you take like x hat and over Z1. So after you do this, you integrate on the cycle such that this converges. So you need to integrate over this cycles. So the integral converges, and now it will depend on the little q and also this Z1 to Zn, and also the input. So to get A side, so you get some like bounded below K theory. There are some characteristic classes which depend on Z1. So if you insert this characteristic class on the A side, it will be equal to this auxiliary integral where you insert the like mirror cycles on the mirror curve, which is mirror to this K-series element. This will be the last lecture for some of the audience. Here, I will just say the proof is because what happens is, we have this. So there's a graph sum formula of omega gn, because omega gn is a unique solution of some recursion. And there's a graph sum formula for this solution. And then we take that graph sum formula and derive the graph sum formula of our FG hat Gn, and also the descendant integral. So we use that graph sum formula to derive the B model graph sum formula for opening invariance, closing invariant, and descendant invariant. And to match it with the A side, we use the genus zero mirror theorem, closed mirror theorem to match the vertex and edges and dilaton. And for the open, we use genus zero open mirror theorem. Yes, to match the leaf contributions. Okay, I'm already very over time. So so I think at least I give you a precise statement and some idea about the proof. If I have